All right, and we're back live. For those of you in the chat, you can't see it, but we have all of our fun. What I don't even know what to call these.
Soon you won't have to go.
That's true. Well, I will. We'll talk about that actually. That's something I did want to talk about, but I don't even know what to call these things actually. So I don't know. So obviously, in terms of if there is a shutdown, and again, some people would argue when, but I'm still going to hold out and say if, even though I have my own opinions. I don't know whether or not they are going to require the teachers to still come into the school building, because what happened last spring, and I won't give away any names. You probably know who they are. But last spring when we went home, I was regularly live streaming for my classes, as many of you know. Of course, there are some teachers that never went live with their students once, and it became an issue with the administration trying to figure out whether or not the teachers were actually doing their job or not. That's kind of where we were stuck. So if there was another potential shutdown, the idea was they would still require the teachers to come into the building. And given that they do, of course, I would still be live streaming at my regularly appointed times. It would just be me in an empty classroom, live streaming to whoever shows up in the chat. Beyond that, if they do say, no, Mr. Markey, you got to be at home, I can still live stream, as, of course, many of you know. I have actually a really interesting setup now because remember I talked about my friend Derek? Derek built me a computer. He built me a computer last summer with some really nice stuff. He built it specifically so I could stream video games. But I can use it to stream high-quality stuff specifically for teaching lessons, which is really nice. So I'd have like multiple cameras set up and stuff like that, like a top-down measure. Yeah, it's absolutely. It'd be really nice. And I could do a lot of different things. But that's if I do it from home. If I do it from school, it would basically be me with this thing right here. It is super neat, I know. Anywho, that's where we're at. I want to pick up where we left off last week, but I want to deal with some of the formulas in the calculator. So what I'm going to ask of you, again, if you don't already have them out, I need the Chromebooks out and open so that you can have the calculators out and open. Oh, no. Trying to think. I don't have an extension cord, but yeah, the calculators are definitely what we need today.
Oh, she's not there.
There you go. The calculators are definitely what you need today because I need to show you how to do various things on the graphing calculator. Now, I am going to show you a couple different ways to do things on those graphing calculators. I am opening up the graphing calculator that is on my phone, and I am bringing out the graphing calculator, the 83s that I have as well. So there we go in a moment. Boom, there they are right there. I'll zoom in. So on the right, you have the TI-83, which is the typical calculator that I have in my classroom. But on the left, I have the TI-84, which is what you guys have on your Chromebooks. So please keep that in mind. Now, last week, we dealt with what is known as the normal distribution. I introduced a lot of things with the normal distribution, the empirical rule, the way that data is typically separated on the normal distribution. And I will review various aspects of that. But what you got to know is that when you do certain calculations using the normal distribution, there are certain functions in the calculator that you need to know how to use. So let's start with this. On your calculators, you have this button that says VARS, V-A-R-S. Now, don't hit that button just yet. But VARS stands for variables. That's not what I'm interested in. What I'm really interested in is what is written in blue just above VARS. You guys have it in blue on your calculators? Sweet. On the 83s, they're written in yellow. So you can see that there on the 83. Above the word VARS, that second function, is distribution. That's where we need to go. So you need to hit second vars in order to see exactly what I need you to see. So everybody hit second vars, and I will take you there. Second vars, second vars. Here we go. This is the screen that you need to be on. There are two specific functions that I need you to be aware of. Two specific functions that we are going to use in this particular unit, which is the second and third function, normal CDF and inverse norm. I don't care for normal PDF. That is not something that you would use at any level of high school statistics. You would mainly use that if you were a statistics major much, much later on into your career. But we are focused on normal CDF and inverse norm. Vars, if here, on your calculator should be the button right here-ish. Yep, and if you hit second vars, it'll take you to this screen. Right? There we go. So the first thing that I want to do is I want to go to normal CDF. And I show both calculators because my calculators are going to show you two different things, but the one on the left, I believe, is what you are going to see on your calculators. If you go to normal CDF on both of these calculators, you will see two different things. Now, my calculator hasn't been reset yet. Let me actually reset my calculator just for the sake of argument. There we go. Is that what you all see? Good. Lower, upper, mu, sigma. That's what this thing is. Normal CDF, and we're going to write this down into our notes later, but normal CDF is attempting to tell you what percent of the data falls between two specific points, a lower limit point and an upper limit point. So, just for the sake of argument, I want you to type in the following. For lower limit, I want you to type in -2. And for upper limit, I want you to type in +2. Under my calculator on the right, the normal CDF, I'm going to type it in like this, -2, (2).
The lower one was -1E99.
Yes, I'm going to talk about that later. Right now, I'm just starting out with some basic numbers.
What is that symbol?
Scientific notation. The capital E on your graphing calculator actually is scientific notation. It means -1 times 10 to the 99th power. I know. We'll get to there. Right now, I'm just starting out with -2 to +2. Now, if you notice on the left calculator right here, oh, I deleted that too. There we go. Mu and sigma, I'm going to keep exactly the same. I'm going to keep mu and sigma exactly the same for the following reason. This is a normal distribution with the mu being 0 right in the middle and with a standard deviation of 1. And last week, when we drew this stuff out, I put in these numbers into one of the more basic normal distributions. And we wrote out some percentages on top of them. And again, we'll copy some various stuff into our notes in a little bit.
You did this with Derek.
Yes, we did a little bit of it with Derek. You know, we also did it with the long jumper versus the shot putter. Mhm. Specifically, we did this with the long jumper, where we drew the normal curve to get that thing out. But now, what I'm really saying when I type this junk in is I'm really saying, okay, what area of the curve is between -2 to +2? That's what's really being asked right now. What percent of the curve is between -2 to +2? Close. You're thinking of the empirical rule from last week, right? The rule from last week stated 68, 95, 99.7. And keep in mind that those were estimates. Those were estimates. Those aren't necessarily the exact number, but those are the estimates based on the empirical rule. But now you have the function on the calculator, which if you did this correctly, which I'm doing up there as well, you should get the exact number. Now, between -2 and +2 should be approximately 95%. It should be approximately 95% according to the empirical rule. But on the calculator, we get the following. I'm going to paste, which you would hit paste on yours, and then you would hit enter, and you would get the exact percentage.
Okay.
You would get the exact percentage. Now, if you notice on my calculator, it had less information typed in on the one on the right.
Mine's different.
Looks a little different. Let me see.
Mine says -2, -2, 0, 1.
Yes, yes. Yours fits, yes, absolutely. Yours fits in a bit more information than mine up here. Yours says normal CDF -2 to 0, 1. Now, oh,
I
what?
didn't realize it was on your phone.
Oh, yeah, I got it on my phone.
This one.
Exactly. This number would be the mu, and this number would be your standard deviation. But now here's the key. If you look at my calculator on the right, on the calculator on the right, I did not type in the 0 or the 1. And if you don't type in the 0 and the 1, then your calculator automatically assumes 0 and 1. Yeah.
It just puts it as a decimal wise, like in the column.
In the column?
Like next to it, it puts like the in decimal form instead of 0, 1.
No. It'll always, the answer you mean?
Yeah.
The answer will always be a decimal for the most part, you know. But it's a percentage. It's a percentage. It's basically saying 95.4% is between these two data points, which is really weird. You can do that with anything, really. If I go back to this normal curve that we did last week, just kind of filling this junk in right here. There we go. I could say, yeah. No, let's do it. Yeah, let me go 0 to 2. 0 to 2. If I went 0 to 2 on my calculator now, which you guys can do as well, if you hit second vars and go back to normal CDF and now change it to be a 0 to 2, I'm going to do the same thing here. Normal CDF, 0 to 2, go down to paste. It spits out that number. What do you notice about the two answers that are in my calculator? What do you notice about this decimal compared to this decimal? It's exactly half. It is exactly half. And it makes sense because literally instead of going -2 to 2, I only went 0 to 2, which cuts that thing in half. It's a very helpful thing when you are dealing with problems that involve a normal distribution.
If you just go by, say if you went down by 1 again, it would just cut that in half?
Kind of, not exactly. It would definitely cut it down. But maybe not exactly in half. And the reason why it wouldn't cut it exactly in half is because, yes, this thing is symmetric, but it's only symmetric around the center. So if I were to go 1 to 2 and get rid of this, they wouldn't be symmetric. It's not the same height. And the thing is, you don't have to like memorize, like, okay, if I do this and this, it's just like as long as you know how to use this function in the calculator, you should be in good shape. Let me show you what I mean. Let me show you a sample problem. Now this problem, as I've always said, this class is the trial version of AP Statistics. It is a trial version. And being a trial version, perhaps sometimes you get to see what the real thing is all about. So let me get to a good problem here. Do. There we go. That should work for me right here. I'm going to zoom in on this one. Ah, come on, IQ scores. Too far. Good. Okay. I'm looking at number 40 right there. Now, this is a textbook that you don't have, but I'm looking at number 40. I want to do this one together. Specifically, I want to do part C together. I want to do part C together first, and then I want to backtrack. Now, part C is talking about IQ score. We talked a little bit about IQ score last week, but IQ is not really the lesson. IQ is intelligence quotient. Don't worry about that. They say, for number 40, based on the normal model, which is what we've been doing this entire time, and they give you these two pieces of information right here. Now, those two pieces of information are your mu and your sigma. It's your mean and standard deviation. They say based on a normal model with a mean of 100 and a standard deviation of 15, describing IQ scores, what percent of people's IQs would you expect to be? And I want to focus first on part C right here, between 112 and 132. Now, there's a few ways to go about this problem. And I am going to put this particular problem, into our notes in a little bit, because I love this problem. But based on this, they're trying to figure out what percent of people's IQs would you expect to be between 112 and 132. Now, just for the sake of argument, they're telling me that it's a normal model. They're telling me that it's a normal curve. They're saying, hey, IQ scores are based on a normal model with a standard deviation of 15. Meaning, you would put 100 right in the middle, and you would go up and down by the same standard deviation.
I thought since the standard deviation was 15, you would put that.
The mean would go right in the middle, the average. Yeah. Exactly. Now, again, we're going to draw this into our notes in a little bit. Right now, I'm focused on the computers and the calculators, But what they're saying is, okay, between, and I'll mark this in black right here, between 112 and 132, between those two black lines, between 112 and 132, what percentage of people would you expect to find? This is the exact type of problem where you would go to your graphing calculators and you would type in the following information. Get that back up here. You would type in the following information. Let's see. I would go, and I want you to do the same thing as well, of course, so you get used to the feel of it all. Second vars, normal CDF. And now, according to this problem, again, going back to this problem real quick, lower limit, upper limit. What am I typing in? 100's your mu. 100's your average. What do I type in for my lower limit and my upper limit? Not 0 to 100. Here's the thing. The lower and upper limit are the area that you are hoping to find. The lower and the upper limit are the area that you're hoping to find. Look what I just shaded in up there in black. I shaded it in black so you can see it. That's the area that they're hoping to find. What are the lower and upper limits of that particular area? Second? Yeah, it's 112 to 132. My lower limit and my upper limit are 112 to 132. Now, I know exactly what you guys are saying about all these other numbers on the bottom. All these other numbers are going to come into play. All these other numbers in orange are based upon the standard deviation. the mu being right in the middle, and adding 15 and subtracting 15. But when it comes to the calculator and what I have to type in for lower and upper limit, I'm going to type in a 112 and a 132. In the calculator on the right, I would type it in as 112, 132. Now, I'm not done yet. I'm not done yet. Yes, definitely normal CDF. Never used the PDF.
What is that?
PDF stands for probability density function or probability distribution function. CDF is cumulative. Cumulative is what we need for this particular function.
It's just two different things.
Oh, yeah. They do two different things. They perform two different tasks. Under mu, I'm going to type in 100. And under sigma, I'm going to type in 15. Because when it comes to the normal CDF, you need to tell it if you have that information. If you have the information in the problem, you need to type in the average and the standard deviation. And I'm going to do the same thing to the calculator on the right. What's nice about your calculators now is that when you go to paste, everything is automatically there in the order that you need it. And it looks exactly like mine on the right. We hit enter, and we get the following answer. Now, this is a decimal. This is a decimal, but of course, this could also be converted to a percentage. The decimal is 0.195. The percentage is 19.5%. And of course, like I said, we'll put that information into our notes in a little bit. I do want to put this particular problem in there just for the sake of argument. But that's how that answer would be, or that's how that question would be answered. That is exactly how that question would be answered. I go back to it. Look at the question. Look at the question. What percent of people's IQs would you expect to be between 112 and 132? And it would be approximately 19.5%. The calculator will do it for you. Any high-level statistics student will have the calculator do it for you. But you need to know how to use it properly. You need to know how to use that tool. Now, before we actually go to our notes, let me show you one more thing here. Check this out. Check this out. Look at this. Look at this. Look at this. I want to answer the part A. I want to answer part A. Look at that. Over 80. What percent of people would you expect to have an IQ over 80? 80 is somewhere here, I guess. And if I'm going over 80, then it would be this shaded region right here. But since it's over 80, it would be all of this. All of this off to infinity. It would be from 80 to some number way down the line. I don't know what that number is. Now, Andrew, you're talking about the scientific notation we were talking about earlier. When you first opened the calculator, you saw -1 E99. What that actually is a -1 followed by 99 zeros. It's an incredibly giant negative number.
That's how they use scientific notation to figure out problems or bigger numbers or something like that?
So to speak. Yeah, so to speak. See, the thing is, I'm actually going to be using the phrase big number in a moment. But the thing is, if I'm going to use the graphing calculator to get this problem done now, this new problem, over 80, meaning 80 or higher, lower limit's going to be 80. My upper limit
Is infinity.
Technically, but I can't type in infinity.
So what would you type in?
I would just type in some incredibly large positive number.
Like 5,000 or something?
Perfect. I'm not even kidding.
Really?
Yeah. I'm not even kidding. Watch what I'm about to do here. Watch what I'm about to do here. I'm going to answer this question. So we're going to go back to the calculators real quick. I'm going to go back to normal CDF here. I'm going to go 80, Whatever that number is. Look what I just typed in.
Yo.
Because here's the thing. It doesn't matter what it is. As long as that other number for this question is just incredibly large. As long as it's incredibly large, it will take care of filling in the rest of that normal curve. And again, we'll go to our notes in a little bit to write this stuff down. I'm going to keep the mu and the sigma exactly the same. I'm going to keep the mu and sigma exactly the same. I'm going to go to paste. Boom. And I get that. Do you get this number?
Yeah, I put it in a different number. I put it in 4 million.
And you got the same decimal that was the answer? That's what I'm saying. It doesn't matter what large number you pick as long as you pick an incredibly large number.
That's crazy.
Yeah. And the answer would be about 90.9% if you rounded it. And that would be about 90.9% of this graph. Here, let me show you something actually real quick. Check this out. Check this out. I'll show you something a little wacky. And I want to ask you your opinion. Check this out. Look at that. Ladies and gentlemen, look at that. Look at that. Look at that. Look what I just typed in. Look what I just typed in right there. I'll move this to the side a little bit. Look at my curve right here that I'll erase this a little bit. What percentage, I'm going to ask you guys your opinion. This is a weird question. But if I'm going from some giant negative number to some giant positive number, what percent of the graph do you think I have shaded in? 99.7 would be approximately if I went from -3 standard deviations to +3. Now, more specifically, for the IQ scores, if I went from 55 to 145, I would have 99.7% of the data points if I went from 55 to 145. But now I'm going all the way to the left, all the way to the right. What percent of the graph do you think I'm shaded in? Sounds like 100% of the graph. Let me go to paste here. Let's see what happens.
There's always something that's not it.
That's true, but here's the thing. Your calculator at some point gives up. Your calculator can only calculate a finite number of things, right? And at a certain point, it's just going to be like, done, round. Watch what happens. Paste.
It just stops working.
Look what it just gave me. Donovan, you said 100%, but I got this. This is 100%. This is. Because remember, it's giving you the answer as a decimal. Remember, we got 90.9%, but it was 0.909. This is 100%. Yeah. Oh, I love it. I love it so much. Okay. Temporarily, ladies and gentlemen, temporarily. I know it's going to be a little weird with the weird kind of things on your desk, but I'm going to need those notebooks out and open. For the time being, how much battery you got left? Quarter? Maybe go plug it in for now, because I may pull them back out if we have time later. Yeah. Boo. Oh, it fell? I'm sorry. Honestly, I knew it was going to happen. Not with you, but I knew it was going to happen.
Nah, he knew it was going to happen. He knew it was going to happen, but he's just trying to make you feel better about yourself.
Did it work? Maybe. Never mind. Goodness gracious.
Somebody's going to break one of these things.
I know. I'm sorry.
I'm telling the principal, he said it.
It's only for a couple weeks before they shut us down.
Do you remember him from middle school?
Yeah, I do.
Okay.
I didn't until I realized who he was. I remember that.
So normal CDF if you were to just type in a lower and an upper and leave the mu and sigma alone, like 0 and 1, this would be a mu of 0 and a sigma of 1. This calculates the percent of data points between two z-scores. If you were to just type it in as normal CDF, lower comma upper, and leave the mu at 0 and the sigma at 1, it calculates the percent of data points between two z-scores. And I've talked about the empirical rule, which I'm going to show you again in a little bit. We wrote down the empirical rule last time. Move that over just a tiny bit. The empirical rule basically stated, okay, between -1 and +1 standard deviations, you should have about 68% of your data points. And I'll come back to this screen in a moment, but let me zoom in right here. Look what I have typed in right here. Between -1 and +1 z-scores, I have about 68% of my data points. Between -2 and +2, I have about 95% of my data points. And between -3 and +3, we talked about this just a few minutes ago, I should have about 99.7% of my data points. And you can see it rounded right there. That's what these things do. If you go any farther with z-scores, then it just like, you were talking about like getting all the data points. Look how close we're getting with 4. And look how close, exactly, look how close we're getting with 5.
And then it just keeps going and then it stops.
Yeah, and then you see at some point the calculator is going to give up and just round up to 1. I believe it's at 7 or 8. It is at 7. Because it's not exactly 100%, but it's like, okay, it's 100%, you know. At that point, you pretty much have everyone on the planet, you know. There's nobody that's going to be that many z-scores above or below. And if you are, then maybe you're an alien. But then what we were doing...
Derek's an alien.
No, actually, Derek is only 2.5 standard deviations. Derek would have a z-score of 2.5, which is unusual, but it's not that crazy. Yeah. Normal CDF, lower, upper, mu, sigma. Yeah, 8 foot would probably put you at like 3 or 4 standard deviations above the mean, which is ridiculous. Yes, it is. Now, if you type in that mu and sigma, it gives you the percent of data points between two data points. And again, I'm going to go back to the IQ example in a moment. If you actually type in the mu and sigma that are given for that particular problem, then it will give you the percent of data points between two data points.
Looks like a slanted 6, the standard deviation time.
It is. It's the Greek letter sigma.
Yeah.
It's, here, hold on. Greek letter, lowercase sigma. If you go to image results, you can see the different variations on it. You know? Yeah, it's a little weird. Like this one, it's like stylized and junk like that.
Yeah.
You know, but it is what it is. Now here's our IQ problem. What I'm going to write down for our IQ problem is this. IQ example. I'm going to put this piece of information. There we go. Yeah, I'll just put that down for now. Check this out. Look at this. Boom. The IQ example was a normal distribution with a mu of 100 and a sigma of 15. This implies that it's normal. This tells you the mu, and this tells you the sigma. Oh, can't see that. There we go. So whenever you see that symbolage, that's what they're referring to. The N is saying, oh, it's a normal model. And the first number would be the mu, and the second number would be the sigma. What's nice about your calculators is that when you go to the interface, it specifically uses those symbols, mu and sigma. So, and then it literally tells you lower and upper. So, yay, happy day.
With your honest opinion, do you think we're not going to, or do you think we're going to shut that? I know, I'm just thinking.
Well, I have been mentioning it multiple times throughout the class period, you know. Honestly, at this point, I don't know. Again, I last year, well, not last year, I'm sorry, it was this year, in March, when people asked me, I told them, I'm like, honestly, I'm not going to pretend like I know because I don't, you know. For all we know, we could be in school through December, and then people are like, how come we haven't gone home yet? You know, and people talk like that, I assume. You know. So now the question on the IQ page, I'll start with part C.
What? It's going to be your fault.
Why can't it be my fault?
Because it's going to be.
Oh, because you dropped the thing. What percent of IQs are between 112 and 132? Now, we already know the answer to this, but I want to just have this written into our notes. What percent of IQ?
Again, unbelievable. So,
That wasn't even my fault this time.
yeah, it's going to be your fault.
No, it actually. Oh my God, now.
Just for you guys listening in at home, she dropped her what was that? What do you even call these things? Desk shield?
Yeah, it's called a shield.
Yeah, it's the desk shield fell again on her desk. Twice.
This time it wasn't, I swear, it wasn't my fault.
Yeah,
Sorry.
it's what the hell's up.
I'm so sorry.
I
So
mean, the first time, yeah, that was my fault. I was gonna hard bind on it, but this time it actually, I swear to God.
okay. Now, if you type that thing in 112, 132, there's your lower and your upper, your mu and your sigma. It has to be in that order. It has to be in that order when you do that particular problem. Normal CDF 112. I already forgot the number, so I'm just going to type in it again. Boom. It gives you approximately 0.195, which they did ask for a percentage, so I would convert it to a percentage, 19.5%. Then, and I am going to do parts A and B as well. They asked a very similar problem, except they didn't say between these two data points. They said anybody over an IQ of 80. And I am going to draw that picture after this particular problem, just kind of visualize this thing together. But what percent of IQs greater than 80? Question mark. What percent of IQs are greater than 80? Now, 100 is average. Just for the sake of argument, I know we talked, I don't know if I talked to both classes about this, but IQ is intelligence quotient. It's basically your mental age divided by your physical age times 100. That's how they determine your IQ. Your IQ is not how smart you are. Your IQ is not how much information you know. Your IQ measures your ability to learn concepts quickly. The higher the IQ you have, the quicker you are able to absorb and digest information.
I always thought it was how smart you were.
Nope, it has nothing to do with how smart you are. You could have the highest IQ in the world and be the biggest idiot. You know what I'm saying? Yeah. And you could have a pretty low IQ, but you could have like so many academic accolades to your credit. It doesn't matter what your IQ is. It just, again, it just measures how well you can absorb information.
I wonder, I want to figure it out. You said like the ones like that people take online are not even.
Yeah, those are garbage. Yeah, those are garbage.
You said you actually have to like pay.
Yeah. So look what I'm writing here. Now, in my calculator, when I did this problem for greater than 80, I typed in like 1 million or 100,000 or something like that, but I'm not going to do that when I write this thing out on paper. And instead, I'm literally going to write out big number. That's sufficient. It literally is whatever big number you decided to type in. So if I'm going to do this normal CDF, I'm going to do it on my calculator right now. Normal CDF 80, comma, some big number comma 100, comma 15. And I'll show you that right here. You can see that. Let me zoom in.
I wrote normal CDF like 20 times.
Oh, yeah. I want you to get used to it. And it's the CDF. Don't use the PDF.
CDF.
Yeah, if you use the PDF, then you're in for trouble. You know, but you can see I typed in some big number. It doesn't matter what the big number is. Like you typed in what, 4,000? Yeah, and I typed in that number. But we ended up with the same answer. It's approximately 0.909 or 90.9%. That's what that thing does. 90.9%. Now, on that problem, they did say under 90. So I do want to answer this question kind of together because we haven't talked about this one yet. Under 90. What percent of IQs are under 90? Question mark. Now, for this one, I want to draw the normal curve. And I want you to draw the normal curve as well. I want you to draw the normal curve as well. So we are going to draw a little normal curve right here. There we go. That's actually a pretty solid normal curve. Look at me. Look at me go. Let's see here. Now, right in the middle, that is your mu. That is your 100.
Oh, that's such a busted curve.
I'm sorry. If I have you do these for like assessments, I'm going to actually have like the normal curve on there. You could probably like print it out and like draw on top of it, you know. So you don't have to worry about drawing a proper normal curve. 100 is right in the middle. That is my mu. That is my mu. And the standard deviation was 15. So again, it's 115, 130, 145. And then down here would be 85, 70, and 55, subtracting those standard deviations. This would be the normal distribution of IQ scores. I'm giving it a title right there. Every picture that you draw needs to have some kind of a title on there. Now it says under 90. So what that means for me is this. 90 would be about right here. This would be where 90 is. Oh, you can't see it. Haha. This would be where 90 is. They want to know, okay, what percentage would be under 90? And if I'm going to be doing under 90, I would be shading in this portion of the graph. And it would go out forever. If I'm going to go under 90. It's kind of nice. So, if I'm going to do this properly, I got to use a normal CDF, as we've done in the past. Let me leave my lower and upper limit blank temporarily. Let me leave my lower and upper blank temporarily. And now I ask you, what in the heck do I fill in for lower and upper?
Whatever you please.
No, it's not whatever I please. It's not whatever I please. I have to do this in a very precise way. 90 is going to be one of those numbers, but which number is 90 going to be? Is 90 going to be the lower or the upper limit? Definitely going to be the upper. 90 is definitely going to be the upper. Absolutely, yes. What do I put for the lower? I can't put whatever big number I want, though. That's what I got to put. First, he said whatever big number I want. I said, nope. And then he corrected himself, and he said, it's got to be a big negative number. Yes, it has to be a big negative number. So I'm going to literally write in big neg number because it's got to be a big negative number.
No.
Negative 10,000. It doesn't matter as long as it's just a big negative number. And then I go to my calculator. Now I had you put your Chromebook so I keep them away, still for the time being. I'm just going to jump back to my calculator so I can show you what this thing does. Zooming in, zooming in, zooming in, zooming in, zooming in. Second vars, normal CDF. There's my giant negative number with a 90 there.
That's one big negative number.
Mm-hmm. That's all you need for this particular example. Some giant negative number. As long as you type that stuff in correctly, paste, enter, it spits out exactly what you need. 0.252 or 25.2%. That would answer that question. As long as you just put in some giant negative number, you'll be fine. And again, like we talked about before, it doesn't matter, how big it is, just as long as it's like way, way off to the left of that curve. Way, way off to the left of that timeline thing. Okay. There's one more function in the calculator that I need to show you. So for the time that we have, because I have roughly 10 minutes, I do want to show you this. Open those Chromebooks back up. Open those Chromebooks back up. I want to show you one more thing.
So these we're done with notes for the day?
Oh, of course. Is that right?
We're done with notes for the day?
Yes, because we're going to write this down next time. We're going to write this down next time. I just want to show you how it works so you have the basis. And then I'll see you on Wednesday. Oh, my word. So
Normally I wouldn't see you till a week later.
see, the thing is, if you can imagine, if this were a normal class period, I would have to be rushing through these formulas, both of these formulas that I'd have to give you and rush. But the thing is, like, now that I actually have like a Monday, Wednesday, Friday routine going on, I can actually like take the time with the information.
Which is better and worse at the same time.
I know, but it is what it is. So on your graphing calculators, I'm going to reset my calculators, both of them, so we can kind of just start at a fresh spot. There's one more thing that I want to show you. Here we go. So I'm going back to the calculators right here. And the thing that I want to show you, oh my gosh, there's a bunch of comments. I'm so sorry. I'm sorry, I didn't see all of your comments till now. What? I know, I'm sorry. They do, or they have to watch the lesson at some point. You know what I'm saying? Because now that they're virtual and I'm teaching 3 days a week. So the thing that I want to show you on the calculator, because again, this class period, I believe, is only till 8:20. Yes, indeed it is. If you hit second vars one more time, second vars, the function that I want to take you to is inverse norm. Inverse norm. Now, just for the sake of argument, when you hear the word inverse, what are you really thinking of? What does inverse mean? What does it mean to invert something?
Why is this in my bag?
I don't know. Why is it in your bag?
Oh, no. I use it for my hair.
Of course. What does it mean to invert something?
That's terrible.
What does it mean to invert something?
Switch.
What do you mean switch?
Flip. Inside out.
That's a good way of putting it. Inverse norm. Oh. She's giving her own commentary. Sorry, in the chat. You guys all can't see it. Anyway, inverse norm is the reverse of normal CDF. Normal CDF will give you a percentage as a result. You type in the data points into normal CDF, and it gives you a percentage. If to invert something means to flip it or do it backwards or switch something, inverse norm is going to do the exact opposite. Inverse norm, you type in the percentage, and it's going to spit back out the data point. Watch what I mean. Go down to inverse norm. If you go to inverse norm, you can see it on both of our calculators right there. It gives you three things. Now, on your calculators, does it say the same thing, area? Is- Oh, okay. Now that's different. Now that is different. Okay. That is definitely different. What's it highlighted on right now? Is it highlighted on left? Good. Keep it there for now. Keep it there for now. That's going to mean something. I'll explain that in the future, but let's just keep it on left tail for now because mine's automatically set to left tail. And so is this one. Now, what that means is this. If I had a normal curve like so, give me a percentage, anywhere from like 0 to 100, but make sure it's like at least double digit. 75%. Let's go 75%. Okay. Actually.
You didn't type anything.
No, I haven't. No, I haven't. Right in the middle is my average. Right in the middle is my 50th percentile. You guys are, I'm assuming a bunch of you have taken the SATs, taken like standardized testing and stuff like that, and you've been given like certain percentiles where you fall, right? If you're in the 50th percentile, that means you're right in the middle. Means there's about 50% of the data that is better than you and 50% of the data that is worse than you if you're in the 50th percentile. If you're in the 75th percentile, like, I don't know where that would be. I mean, I do know where it would be. But let's just say this is the 75th percentile right there. That's what you're suggesting. Let's find out what the 75th percentile of IQ score would be. The 75th percentile of IQ score. Now, you said that the calculator set to left tail. Don't change it. Don't change it. Keep it left tail. And what we're going to do is this. 0.75. You would have to type it in as that decimal. Make the area 100 and make the standard deviation 15. Because we're sticking with IQ scores for the time being. If I were to do it on my calculator, I would actually have to type it in like that. That little U next to the 100, that is the Greek letter mu. Mu. Yes, that is your average. That is your population mean. Yes. And that weird sideways 6, as we said before, that's the Greek letter sigma for the population standard deviation. Yeah, or average deviation from the mean. Now, if I hit enter on this, if I hit enter on this, all this stuff, it's going to give me some information. When you go down to paste? Oh, just click down. Did it work? Okay. That's okay. That's okay. Now, I want you to think about this for a second. Think about this for a second. Normal CDF, you type in the data points, it gives you the percentage. Inverse norm, you type in the percentage, it spits out the data point. That's exactly what it does. It does the inverse of normal CDF. What this means is, well, if I have an IQ of about 110.1, it means that I lie at the 75th percentile of data points. Or if I'm at the 75th percentile, remember how you said it was left-tailed? If I'm at the 75th percentile, left-tailed means that I'm better than 75% of people. Yeah, if you did it right-tailed, it would actually give you the data point where 75% are better. No, center would mean you're in the middle, the data points that would give you the middle 75%. It's weird because if you did center, it would actually give you two numbers, which is weird. We're going to stick to left for now. Doing center and doing right would be a little bit more complicated for what we're hoping to do. But, I love problems like this. The whole point of this unit with normal CDF and stuff like that is to be able to properly calculate problems like this. We're going to get into these details. Oh man, if only I was going to see you more times this week. If only I was going to see you more times this week, because we ran out of time, ladies and gentlemen. It's 8:19. I don't know what to do. Oh well. I don't know if any of you can come back on Wednesday.
No, I don't think so.
All right, yeah, you might be able to make it. Yeah. All right, okay. All right. You let me know. You let me know. Anyway. Of course. Okay, I'm gonna sign off, and we'll pick up with this on Wednesday. I mean, if we're all still alive. Yeah. All right. Bye-bye. That's true.